start recording. We usually record the talks, and please, Richard Szabo is our long friend, and we are very happy to have him today here at these seminars online. He will speak about a new look at symmetries in non-commutative field theory.
Okay, thanks for the introduction, Paolo, and thanks to all the organizers for asking me to speak at this series. So we'll see how this goes. I'm not a big fan of these online talks because when in the past when I've spoken, I usually like to pace around a bit, and if I pace around now, it doesn't. It somehow doesn't work. Not just because my room's too small, but it just gets a bit weird. Right. Anyway, so what is this talk about? So the organizers kind of gave me rigorous instructions about how the talk should be structured. So one of the criteria was that it should be a talk with a physics content. And I sort of got a little depressed when I started thinking about that because I sort of started feeling a little bit disconnected from physics. So the presentation I'm about to give is certainly geared at physicists. It's not geared at mathematicians. So I won't be going through a lot of the formalities, and there is a lot of interesting mathematics underlying what I'm going to say. And certainly the problem I'm discussing is a problem that is of interest in physics. So I'm going to explain that. And the other requirement was that, I don't assume that everybody knows everything about, non-commutative theories. So I'm going to give some brief review or just some indications of what's been done in the past by ways of motivation of what I'm doing. So can you see my mouse here when I move it? Can you see that?
Yes, we do.
You can see that? Yeah, okay. That's the only pointer I have. Okay, so the structure of my talk, I'm going to spend a bit of time motivating when I'm going to speak about, and I mean roughly half of this talk is going to be, based on commutative theories, because one of the points of what I want to say about gauge symmetries and non-commutative field theories is taking a look at them from a somewhat more modern perspective. This more modern perspective is based on these mathematical gadgets called homotopy algebras, and in particular in this case L-infinity algebras. So I'll spend a bit of time explaining some of the background from commutative classical field theory on how some new understanding we have about how to think about gauge symmetries. Then the new look I'm going to give at gauge symmetries in non-commutative field theories will be based on something I'm going to call a braided gauge symmetry. Okay? And corresponding to these braided gauge symmetries, which will be some kind of deformations of ordinary gauge symmetries, there'll also be a deformation of this homotopy algebra structure that I'll explain, and it's called the braided L-infinity algebra. So roughly the first half of my talk will probably be taken up by these first two items here, and then we'll sort of get into the meaty, interesting issues. And I'm going to finish with an example. So I'll do a lot of formalism, and I'll finish with a very concrete and interesting example of a new type, new version of non-commutative gravity in 4 dimensions that I'm going to call the braided non-commutative gravity. Okay, so this talk is based on a recent paper, just came out about a month ago in collaboration with Maria Dimitrovic-Širić and Voja Radovanovic in Belgrade, and Gregory Diotopoulos, who's a PhD student in Edinburgh. Okay. So what is the problem that we want to face? So because there's a diverse crowd here, possibly some mathematicians. Let me just say what I mean by a non-commutative field theory. But for me, a non-commutative field theory is going to be a field theory that is a deformation of a classical theory. So you give me a scalar field theory, you give me classical Yang-Mills theory. That's defined on some manifold. I imagine I can deform the algebra of functions, the exterior algebra of differential forms, and any other spaces of fields on them by some means of some star products. Okay, so I can deformation quantize my classical field theory into a non-commutative field theory. So that's what I mean by non-commutative field theory, whereas the notion of say a non-commutative Yang-Mills theory can be made a little more general, just that. And so indeed, in particular, what's been of interest for many years, and in particular, if you're interested in string theory, are non-commutative gauge theories, such as non-commutative Yang-Mills theory. Yet after over intensive years of work, spanning over 2 decades now, since these models became of interest in string theory, there's still many general problems which we don't understand in how to properly build up a non-commutative gauge theory. Okay? So if we're content in working on spaces where we can deform, quantize to give us, say, something simple like the Moyal product, then we understand quite a bit. And you might even say we understand everything, but in general, we do not understand many things about how to construct these theories. So 2 of the issues involved are, first of all, with gauge transformations in these theories. So let's suppose you have something very simple. Let's look at a gauge theory with a U of 1 gauge group. So there's a gauge connection, which is a 1 form. There's a function, which is a gauge parameter called lambda. And I just define a very, very naive notion of a gauge transformation. Then I'm going to call star gauge transformations. Okay, so I'm going to speak about this in a little bit more detail later on, but we just write down this naive transformation law. I'm not telling you what star is. It's some associative star product. I might get it from quantizing a Poisson structure on my manifold, but I just write this down. And it's just the basic fact that, except for simple examples, such as the Moyal product, these gauge transformations will not close. Okay? So if you take the commutator of a pair of gauge transformations, it will not close under this star product. Okay? That's just a calculation that you do. Another related issue is, of course, when we're building up field theories, we want to construct a differential calculus on our non-commutative algebra. And just the ordinary exterior derivative is in general not a derivation of a star product. Okay? So in other words, the Leibniz rule does not hold. So this is a problem that's been addressed from many points of view over the past 20 years, and I don't have time to review all those approaches, but this is one of the things we're sort of glaring at when we start to think about non-commutative gauge theories, and in general, symmetries of non-commutative field theories. So on a related note, which is a big inspiration for what I'm going to talk about, is the problem of constructing a theory of non-commutative gravity. So there's, again, a lot of work that's been done on this over the past, for more than 15 years now. And there's a lot of successes to this approach. But in the very general case, again, in particular, if I'm looking at theories that carry non-associative star products, which is something that has been of interest lately, it's not known in general how to construct a metric theory of non-commutative differential geometry. So in other words, there's no general version of the Einstein-Hilbert theory for non-commutative gravity. And so, of course, an old idea is to, well, let's not think of gravity as based on non-commutative Riemannian geometry, but let's try to think of it as a gauge theory. And there's a way to do that using the Einstein-Cartan formulation, and then writing down a corresponding action functional for that, which is the Palatini action. So there's so much work on this, it's impossible for me to give references to everything that's been done in the past on these theories. So please excuse me if you're in the audience and your name is omitted from several lists that appear here. Okay, so on the one hand, we don't understand the metric aspects of non-commutative geometry. On the other hand, we have this kind of gauge theory, way of thinking about gravity, and we could try to deform that. Right? What you're faced with, of course, when you do that is in this theory, this Einstein-Cartan type formulation, that there are two types of gauge symmetries. There are, of course, the local Lorentz symmetries, which look like conventional gauge theory, but there's still the diffeomorphisms, which have to be taken into account. Okay, so we'll talk about this a bit more as we go along. Now, fast forwarding many years, what was noticed a few years ago is that there is a mathematical tool that offers a natural framework for dealing with non-commutative gauge theories. And that's based on these things called L-infinity algebras. And I'll try to explain a bit what these things are, because I think in this crowd probably doesn't know much about those. But this has been the proposal, that these are things which first of all can control things such as this gauge closure problem that I mentioned, and they can also control violations of things like the Leibniz rule. And if I'm interested in non-associative deformations of a theory, they also account for violations of the Jacobi identity. Okay. So there is this approach based on L-infinity algebras using these conventional star gauge symmetries that I wrote down. However, what's lacking in these theories is that it's a very complicated construction. Not all the structure functions of the L-infinity algebra are typically known, and what most importantly, the construction is limited to the semi-classical level. So the semi-classical limit of a deformation quantization of a Poisson manifold is just a gauge theory that's based on a Poisson bracket. Yeah. So the theory is limited to that. So if you want to think concretely, if you're expanding things in your deformation parameter, you call it theta, then this is only understood well up to leading orders in theta. So this is something we'd like to overcome. So what are these L-infinity algebras? And I just want to quickly flash this slide to indicate the idea is actually not new. The history of L-infinity algebras in physics go back to work from the 80s and higher spin gauge theories, where it was noted that higher spin gauge transformations close up to a generalized notion of closure. Namely, they close with these things called field-dependent gauge parameters. Okay. And some years later, there are these so-called generalized gauge symmetries that appeared in closed string field theory. These are complicated gauge symmetries that involve an infinity of brackets that I denote by these symbols Ln. And this was really the first appearance of the full L-infinity algebra structure in physics. So the mathematicians picked up on this, realized these were things that were known in the literature, the mathematics literature. And in deformation quantization, L-infinity algebras are also known to play a role. The famous Kontsevich formality theorem, it's not based on L-infinity algebras, they're based on looking at a type of isomorphism of differential graded Lie algebras. So differential graded Lie algebras are special examples of L-infinity algebras, and the whole framework of Kontsevich's formality theorem is based on these so-called L-infinity quasi-isomorphisms. But what's relevant here is that any classical field theory that has symmetries, local gauge symmetries, and I call them generalized gauge symmetries because they do not have to be gauge symmetries that are associated with, say, a principal bundle. They don't have to be associated with connections of some bundle over your manifolds. So they're just local gauge symmetries, and any classical field theory, any, let's say, polynomial, any theory with polynomial interactions has its symmetries and its dynamics which are determined by an L-infinity algebra. That's a fact, and that fact is based on another fact that this L-infinity algebra formalism is dual to the BRST formulation of these generalized gauge symmetries. And I'll say a little bit more about that as we move along. Okay. So that's the basic fact. And this is the idea that was trying to be applied in the non-commutative world. Okay. So what are the goals now? So as I said, one of the inspirations for thinking about this new thinking about symmetries was to think about trying to fit the symmetries of gravity into this. And as I said, we can think of gravity as a gauge theory, but we have to, when we think about the Einstein-Cartan formulation of gravity, we have to confront ourselves with the diffeomorphism symmetry. And as I'll mention later on, the way that we understand how to implement diffeomorphism symmetry in the non-commutative world is by things called twisted diffeomorphisms. And twisted diffeomorphisms do not seem to fit nicely into the standard picture of L-infinity algebras, namely the picture that's been advocated where we look at the gauge symmetries through star gauge transformations. So the idea then was to deform not just the theory, the field theory, but also deform this L-infinity algebra structure. And this will bring about a new type of homotopy algebra structure that we're going to call a braided L-infinity algebra. So what I'm going to do in this talk is I'm going to work towards defining some new deformations of field theories with things I'll call braided gauge symmetries, and then explain how these are formulated naturally and systematically through a general notion of braided L-infinity algebras. And hopefully if I do my timing okay, we'll come to an example of a new deformation of a new type of non-commutative deformation of gravity at the end of the talk. Okay. So this is the goal. This is the goals of what I want to try to explain here. I want to give a bunch of disclaimers now of what I want to say. So this will perhaps kill off a bunch of potential questions at the end. But I also want to say a few words because I don't want to upset anybody, okay? So the first disclaimer I want to make is I do not claim that the notion of braided gauge symmetry that I'm going to talk about is truly new, okay? A lot of the kinematical aspects of this idea have appeared before, work by Brzezinski and Majid, for example, and several follow-up works. And indeed, a lot of the ideas and techniques that I'm using here are borrowed from the work on twisted non-commutative gravity. What will be new is the way that this is implemented to describe the full dynamics of non-commutative gauge theories in general, and also the use of these new homotopy algebraic structure, these braided L-infinity algebras. So these aspects I do claim are new, but I don't want to set off that the buzzword braided gauge symmetry is our own. The second thing I want to say is I'm going to talk about strictly classical field theories here. I have nothing to say yet about the corresponding quantum field theories. This is something that is being looked at from several directions, but I don't know anything about them now. Everything I say in this talk will be classical, and that's really the extent of my knowledge. Excuse me. There is work from many years ago by Robert Ockel, where he talked about braided quantum field theories, and I would expect that the quantization of these theories is somehow related to that. But Ockel doesn't talk about braided gauge symmetries. He's just got a kind of combinatorial formulation of non-commutative field theories that he calls braided quantum field theory. But indeed, there should be some relation to that. In this talk, I'm only going to talk about diffeomorphism invariant field theories, just for simplicity. There's no problem in going and looking at more kind of physical theories like Yang-Mills theory or scalar field theories. They also fit into this framework. I'm just not going to discuss them. And well, it's non-commutative geometry and physics, this seminar series. What are the physical realizations of what I'm going to talk about? I don't know. I don't know yet. This is something to look at, to do these types of theories have any realization in string theory or any other models of quantum gravity or even effective theories of condensed matter physics. I don't know yet. This is something that's left open. So this is just a pure talk about constructing new types of theories and new types of symmetries. Okay, so this is the introduction, which is a bit lengthy, I see, but okay. So I'm going to start off in the classical world, and let's first think about what is a gauge symmetry. Okay, now I'm not asking this to be, you know, to be condescending or think that nobody here knows what a gauge symmetry is, but there's a point, and this is going to be a point for comparison to what I'm going to say later on about braided gauge symmetries. So let's look at a very, very, very simple example. So take a three-dimensional manifold M, it's oriented, has no boundary, and let's consider Chern-Simons gauge theory on this manifold, okay? So I picked some Lie algebra, and I want this to be a quadratic Lie algebra. So I want it to have an invariant non-degenerate pairing, which I'll denote by a trace. And if you want to think of G as a matrix algebra and TR as the matrix trace, that's fine. Then the Chern-Simons action functional for a gauge field, which is a one form valued in this Lie algebra, looks like this. Okay. This is just the Chern-Simons action. A very simple theory. And we know this theory is invariant under the standard gauge transformation. So you take a function or zero form on M that's valued in the Lie algebra, and you define a gauge variation of A by this. Okay, and so if you apply this variation to this action functional, it's invariant. Okay, the Euler-Lagrange equations, if you vary the action with respect to arbitrary variations of the gauge field, are very simple. They just tell you that the curvature 2 form of this gauge field is 0. Okay, so these are flat connections whose curvature is 0. And the curvature of this gauge field is also a covariant object. So if I apply this gauge transformation to the curvature, then it transforms covariantly in this sense. And because of this rule and the calculation, this tells you that the gauge symmetry acts on the space of classical solutions. So namely, if I have a formula I can compute, I just take A, apply a gauge variation to it, and then what I'll find is that the corresponding field strength can be written in terms of the field strength of the original gauge field plus the gauge variation of that gauge field. So if A is a solution of the field equation, so FA is 0, then because FA transforms covariantly, we also know that delta lambda FA is 0. So that means that if A is a classical solution, then so is A plus delta lambda A for any gauge parameter lambda. So this is what we mean by that there are gauge redundancies now in the classical degrees of freedom. And so the space of physical states, and I mean the classical physical states, is the moduli space of classical solutions, which in this case are the flat connections, modulo gauge transformations. Okay. So this is what I mean by a classical gauge symmetry in this talk. So there's another way to think about these gauge redundancies in the theory. So let's go back and look at the action. Let's go and suppose we try to show that this action is actually gauge invariant. So if you do the calculation, you vary S, you find that you can rearrange it into this form here. So you can rearrange it into a form which is delta lambda of A, the gauge variation, wedged with the curvature 2 form. And that's because a gauge transformation, a gauge variation is just a special case of a general field variation. And if you were calculating what the Euler-Lagrange equations were, you would do exactly this type of manipulation, except you would look at an arbitrary variation of the field. Okay? So the same argument works with the gauge variations in this case. Well, what you can do now is use the formula for the gauge variation, do an integration by parts, use the invariance property of this quadratic form here, and rewrite the variation of the action S in this form now. So it's an integral of the trace of lambda times the covariant derivative of FA. Okay? So this dA/FA is just the gauge covariant derivative of the curvature 2 form. That gives us a 3 form on this manifold valued in the Lie algebra G. Okay? But what else do we know? Well, we know, without even thinking about gauge invariance, Chern-Simons theory or anything, we know that the curvature 2 form satisfies the Bianchi identity. Okay? So the curvature, the covariant derivative of the curvature is just automatically 0. Okay? If you didn't know that, you would read it off from this identity up here, because if you know that the Chern-Simons action functional is gauge invariant, then you know that because of the invariance of the the non-degeneracy of the pairing up here, that if this holds for arbitrary gauge parameters lambda and delta lambda s is 0, then the Bianchi identity would have to hold. So the Bianchi identity in this theory is equivalent to gauge invariance of the action. And this fact is just a very, very simple example of a more general statement in field theories with gauge symmetries. Okay, so we're all probably very familiar with Noether's first theorem, which tells us how to compute conserved charges given symmetries of a theory. This is Noether's second theorem. And Noether's second theorem says that the local gauge symmetries of a field theory are in one-to-one correspondence with differential identities among the equations of motion, or more precisely among the Euler-Lagrange derivatives of that theory. Okay? So these are identities that we'll call Noether identities, and the point is they hold off shell. Okay? They're really identities. They're just differential identities. And just like the Bianchi identity is something which is true regardless of what the classical solution space of this theory is. And this is just another way to understand what the gauge redundancies mean in this theory. So these differential identities are called Noether identities, and these are what exhibit the interdependence of degrees of freedom in your theory that are due to gauge symmetries. Okay. So apologies to all of you who know this, but let's look at one more thing here. So one other key point about this simple example of Chern-Simons theory is to note the ingredients that went into describing the classical theory. There were 3 things essentially. First, there was a graded vector space, okay? So which is basically the exterior algebra, the vector space underlying the exterior algebra of my manifold. Okay, so I take the P forms where P runs from 0, 1, 2, 3 because it's on a 3 manifold, valued in G. Okay, so P equals 0, the 0 forms, remember these were the gauge parameters. The 1 forms were their fields or gauge fields. The 2 forms were the field equations or the Euler-Lagrange derivatives, which were the curvature 2 forms of our gauge fields. And the 3 forms are where these Noether identities left. Now on this graded vector space, how did I construct the equations of motion and the Noether identities? I defined operations, and I'm going to call these brackets. So there was a 1 bracket, which was the Derham exterior derivative. There was a 2 bracket, which was just the Lie bracket extended to these differential forms. So the exterior derivative, L1, makes this graded vector space V into a cochain complex. It's just a Derham complex with values in this Lie algebra. And it's a derivation. It's a derivation of this Lie bracket extended to differential forms. And as I said, L2 itself is a Lie bracket. It's a graded Lie bracket on these. So it comes with a grading, where the grading is determined by the form degree here. So in other words, it's antisymmetric, graded antisymmetric, and it satisfies a graded version of the Jacobi identity. And that's all I need. These were the building blocks of the classical moduli space of Chern-Simons theory. Now, if I ask that theory actually comes with a Lagrangian description or variational principle, then I want to construct an action. And the action in that theory was constructed by pairing the field A with the brackets L1A, L2 evaluated on 2 slots through this, what I call a cyclic pairing. So this defines a non-degenerate bilinear pairing on this graded vector space. Okay. So that's mathematically what I used to construct Chern-Simons theory. So the first 2 items there define a structure which is called a differential graded Lie algebra. The third structure is an additional data on this differential graded Lie algebra, which makes it into a cyclic differential graded Lie algebra. So what this is telling us is that Chern-Simons gauge theory is organized by a differential graded Lie algebra. And this is is the prototypical example of a more general statement, which says that any classical field theory with generalized gauge symmetries, some sort of local gauge symmetry, is organized by an L-infinity algebra. So what is an L-infinity algebra? So usually in physics, we write this down by writing down an infinite sequence of operations, of n-ary operations, together with a lot of complicated looking relations. And that is one incarnation of them. But let me give you a sort of, 2-line definition of what an L-infinity algebra is, which is, I guess, the way mathematicians like to state this. So you take a graded vector space, so it's a z-graded vector space. You shift what you mean by the degree by 1. That's what the bracket means here. So it's a shift in degree by 1. And you look at the exterior algebra, just the ordinary vector space exterior algebra of that shifted vector space. Okay? And this can be viewed as a co-algebra with a co-commutative co-algebra structure. And on this, I place a map, a linear map, which is a co-derivation. Okay? So this is kind of, the co-algebra world of what, we like to think of as, algebra derivations of that. The map has degree 1 and it squares to 0. Okay? So that's an L-infinity algebra. Now, the way we like to think about this, or rather the way I think in physics that we construct these things, is because this L is a co-derivation, it's uniquely determined by what happens to its image inside V of 1 rather than the whole exterior algebra. So we can break it down into components, which you can think about as kind of Taylor series exponents, that I'll call these LNs, where these are all maps of degree 1. Or if we shift the grading, get rid of this 1 here, and just view these as maps without the degree shifted, then these are maps of degree 2 minus n. Okay, so they're multilinear maps. They're antisymmetric because they come from the nth exterior algebra. And the equation now, the condition that L squared equals 0, gives you infinitely many relations among the different maps. So the first few look like this. The first one tells you essentially that L1 squared is equal to 0. So that tells you, because L1, you see by this degree formula, has degree 1, it tells you that it makes this graded vector space into a cochain complex. Okay, so just always keep in the back of your mind what I said about Chern-Simons theory. This is what we're generalizing here. The second relation that comes out tells you that L1 is a graded derivation of this bracket operation, this graded antisymmetric operation L2. And again, just think back to what we saw with Chern-Simons theory. So this is just, again, a generalization of that. And the new things now start happening at level 3. Okay, so there's a sort of homotopy Jacobi identity. So on the left-hand side of this relation, I write down what would be the combination that would be 0 if the graded Jacobi identity for this bracket operation held. But now I allow that to be violated by some combinations of this L1 and this L3 bracket. So I think of that as a kind of homotopy violation of the Jacobi identity, or the Jacobi identity up to some homotopy, and so on. Okay? There's going to be an L4 bracket, L5, L6, and then a whole infinite tower of higher homotopy Jacobi identities. So that's an L infinity algebra. And you think back again to the Chern-Simons example, or just in general, L infinity algebras are then generalizations of differential graded Lie algebras. So a differential graded Lie algebra would be an instance of this structure where only the brackets L1 and L2 were non-zero. L3 and higher would be zero. That's a differential graded Lie algebra. And so the final structure that we talked about in the Chern-Simons example was the cyclic structure. So a cyclic pairing on an L infinity algebra, which makes it into a cyclic L infinity algebra, is a non-degenerate graded symmetric bilinear operation that satisfies a type of cyclicity condition. Okay, so this is just saying that if I take V0 and I roll it into the first entry of any of these brackets Ln, then I can shift Vn out and make this replacement with some prescribed sign factor in front. Okay? So that's a cyclic structure. And so cyclic L infinity algebras generalize the structure of quadratic Lie algebras. Okay. So this is what we need to understand about L infinity algebras. So I was going to explain a bit the connection with the BV formalism, but I think I'm going to skip most of that because I'm running brutally slow as usual. But what do these L infinity algebras have to do with classical field theory? So just a few seconds mentioning this. Well, it has to do with the BV formalism. And if you don't know the BV formalism or are uncomfortable with hearing those words because it's sort of something very complicated, then don't worry, you don't need to know the BV formalism in this talk. But I just want to mention that the BV formalism naturally organizes the fields of a theory into vector spaces, and from the BV operations I can read off these L infinity brackets. So this is the basic fact that when I think about a field theory, going to organize it into a complex that has 4 basic graded components: a space V0 that will always contain the gauge parameters, a space V1 of fields, a space V2 where the field equations will live, and then a space V3 which will contain the Nether identities of my theory. Okay? And you can extend this more to include higher gauge transformations, which would mean you're dealing with a theory that has reducible gauge symmetry. So there are also redundancies among the gauge parameters of the theory, but I'm not going to look at any theories like that. But what is the outcome from this? When we apply this BV formalism, we can write down a kind of recipe for how to construct a classical field theory given a L infinity algebra. So the gauge fields, the fields of my theory always live in the space V1, and they're transformed by a gauge parameter according to this prescription here. So this is something I define. So I take my first operation L1 on lambda, I take my binary operation L2, I fill one slot with the gauge parameter, the other with A, and so on. There are in general infinitely many terms in this sum, depending on the L infinity algebra that underlies this theory. Okay, and you just keep adding, L3 will have a lambda and the other 2 slots filled with A's. And then there's a statement that follows from these higher homotopy Jacobi identities, which will guarantee that this gauge algebra closes. It might close up to one of these field-dependent gauge transformations, but it indeed closes. And for the experts out there, I'm only talking about gauge symmetries which close off shell. So you can write a more general closure relation that only holds on shell. So the field equations from this prescription also follow a pattern. So we take again our L1 and our L2, our L3, our L4, and we just start filling the slots with these A's. Okay, I don't want to write the general formulas because I'm not going to need them. Okay? And then the homotopy Jacobi identities, again, guarantee that this is a covariant object. Okay? So the things which dictate the field equations transform covariantly, but again, in a sort of higher sense. Okay. And then the final thing that the homotopy Jacobi identities of this L-infinity algebra guarantee are the Nether identities. So the Nether identities are again going to be some infinite sum of combinations of the field equations and the gauge fields, and it vanishes identically. It's just an identity. So this is what was the Bianchi identity in the Chern-Simons action, but it's identically zero off shell. And then finally, if we're given a cyclic structure on our L-infinity algebra, then I go and construct an action functional whose variation will produce the field equations, and which will be gauge invariant. It will be gauge invariant because I can write down this kind of integration by parts identity, and because of the Nether identities, which are identities, they just vanish off shell, the action is gauge invariant. Okay, and again, there's the generalized gauge transformations in this sense act on the field equations. So there's a well-defined moduli space of field equations modulo the action of these gauge transformations. Okay, so that's the classical theory. So let's now start going to the thing of interest, which is gauge symmetry, non-commutative gauge symmetries. Now we're going to look at star products later, but I'm not going to write down a lot of examples of star products. So the classic example to keep in mind is the Moyal-Weil star product. Okay, if you want to be concrete, just think that we're working on M equals RD with a constant antisymmetric bivector, and we look at the standard Moyal product. So just think about that for definiteness now. Again, now suppose we have some matrix Lie algebra. We define a gauge parameter, which is a function valued in that matrix Lie algebra, and we take a one form, which is valued in that matrix Lie algebra. And then what I mean by a star gauge transformation is just what I said at the start of my talk. It's just a naive deformation of a classical gauge transformation. So it's just given by this formula, where this star bracket here just means the commutator, but with the star product and combined with matrix multiplication between the two entries. So the problem with these is that these do not close on the matrix Lie algebra in general. Okay, so firstly, this quantity delta lambda star A doesn't have to be valued in the Lie algebra again. And moreover, the gauge variations do not close on G. Okay, so you can still derive this identity for the commutator of these gauge transformations, but this star commutator of lambda 1 and lambda 2 is in general not valued in the Lie algebra. The exception to this is when G is the n by n permission matrices in the fundamental representation. Okay. In general, these do not close. So how do we close star gauge transformations? And this was a massive topic over 20 years ago. Well, one observation is that they don't close in the Lie algebra G, but they do close in the enveloping algebra, the Lie algebra G. So if you want the formal series of powers in the Lie algebra elements. Okay? So if we extend everything to be not valued in just the Lie algebra G, but also in the universal enveloping algebra of G, then the closure is okay. The problem with this is this will introduce new degrees of freedom in the theory, and for a general Lie algebra, it will introduce infinitely many new degrees of freedom. New degrees of freedom in the sense when I try to expand in a basis. So this is not a theory that has a kind of good classical limit, because when we take the classical limit, we want to end up with our classical field theory that we're deforming. Okay? So that's the problem with this. So one way out of this is through the machinery of Seiberg-Witten maps. Okay, so the Seiberg-Witten map relates non-commutative gauge orbits with classical gauge orbits. Okay, so if we denote all our non-commutative parameters with hats, then the Seiberg-Witten map is an equivalence of this type. It says that there's a map from a classical gauge orbit, A plus delta lambda A, into a non-commutative gauge orbit where the gauge parameters also depend on the gauge fields A. So in this type of formulation, no new degrees of freedom appear, but we get a sort of interesting theory now with lots of new interactions. Okay, and this has been something that's been of interest in the non-commutative phenomenology, if I can call it that, and people have worked on this a lot. The problem with this is that the Seiberg-Witten map is in general not known in closed form. Okay, so at best one can use this map as an asymptotic series and work out the first few orders in an expansion in the non-commutativity parameter theta. So that so some people might not think that's a big problem. I'm highlighting that as something that I don't want. I don't want to write down expansions in theta. I want to try to write down things exactly. And what about gravity? Well, I mean, the same type of argument shows you if you take a pair of vector fields, then if you define a naive star commutator of two vector fields, the result is not a vector field again. Okay? So again, it's something that should be thought of as an enveloping algebra valued object, but now there's no analog of the Seiberg-Witten map for these deformed diffeomorphisms. So we can't sort of use the same game as above. And what was realized, in fact, that the natural definition of non-commutative diffeomorphisms uses twist deformation techniques. Okay. And that's what I want to come to next. Okay. So I have I could spend about 20 minutes trying to review for non-experts what Drinfeld twist deformation quantization is. I've condensed it into one slide, so I'm going to be extremely brief about what this machine does, but there's of course a lot of layers underlying what I'm going to say here. Okay. So let's take the space of vector fields. Okay, the vector fields on a manifold. Okay, I'll write this as gamma Tm. So that's a Lie algebra with the usual Lie bracket of vector fields. So I can look at the universal enveloping algebra of that. This is a Hopf algebra. The universal enveloping algebra of any Lie algebra is a Hopf algebra. And I can define an object in there called a twist, a Drinfeld twist. Okay? I'm not going to write down what that means. It means that it satisfies a certain co-cycle condition in the Hopf algebraic sense, and it's usually given some normalization condition. But I'll write the legs of the twist in this tensor product in this notation, this F alpha tensor F lower alpha. So an example would be the Moyal-Veil twist. Okay, so this will be the twist that ultimately describes the non-commutativity with the Moyal-Veil star product. Okay, so this is a concrete example to keep in mind. And then these legs F alpha that I write here would come from expanding this exponential as a formal power series in these derivative operations. Okay. So if I take any enveloping algebra module algebra, okay, so in practice, this is going to mean functions, forms, tensor fields on my manifold, then the Lie algebra of vector fields, of course, acts on such an algebra by Lie derivatives and the Leibniz rule, and hence so does the universal enveloping algebra. So that's what I mean by a U gamma Tm module algebra. It has an action on the algebra. And given this twist, A is an algebra, so I can deform its product. Okay, so if I just call its product universally with a dot symbol, then I use this definition of a star product. So I take A tensor B, I apply the inverse of my twist element to it, and the inverse I can expand out. Similarly to F, I put bars on the legs of the twist, and this is my formula for twisting it. And the fact that this is a Drinfeld twist, it satisfies a co-cycle condition, guarantees that this is an associative product. So this defines a noncommutative algebra, and it carries a representation of not the original Hopf algebra, not U gamma Tm, but of a twisted Hopf algebra, UF gamma Tm. Okay? And that acts covariantly on any of these star products via a twisted coproduct. Okay? And I'm not going to write out what that twisted Hopf algebra looks like. It's not so important for following the gist of my talk, but this is the basic principle of this deformation quantization procedure. Now, if the original algebra is if the original algebra A is commutative, then this deformed algebra is not just arbitrarily non-commutative, but it's braided commutative. So if I try to swap B and A in this formula, I can do that, but I accompany it with these R matrix factors. So R here is the inverse of F to the power 2, and I'll again write its legs in this notation, this R upper alpha tensor R lower alpha, and when I use the inverse R matrix, I'll put bars on these R's. Okay, so it's braided commutative, and this is where this word braided is coming in. It's not arbitrarily non-commutative, but the non-commutativity is controlled. It's controlled by this R matrix. Okay, so that's it. That's the crash course on Drinfeld twists. Okay? But this is really the take-home message of what, at the bottom here, of what this quantization does. It gives us a braided notion of commutativity. Okay, so let's start looking at this thing I call braided gauge symmetry. Okay, so it's actually quite simple now. So whenever I have an object that's acting on two or more fields, I twist it. This is the whole principle of twist deformation. So I can take, if I take a Lie algebra, and I look at functions valued in that Lie algebra, that would be a Lie algebra on its own, but I can take the Lie bracket now and twist it according to this prescription here. Okay? And I get some other type of bracket. Okay? That's no longer a Lie bracket. You no longer get a Lie algebra, but you get something called a braided Lie algebra. Okay? So the quantity you get is no longer antisymmetric, but it's braided antisymmetric. Okay? So you see this is this braided world where whenever you swap two things, you have to accompany it by factors of this R matrix. And the Jacobi identity doesn't hold, but there's a braided version of the Jacobi identity, which I've written in this line here. And the intuition behind this formula is simple. When I write the Jacobi identity, what do? I take this triple bracket and I want to group it now in two different ways. I want to first group lambda 1 with lambda 2, which is what I do here. And then I want to add to that lambda 1 bracketed with lambda 3. But to do that, I have to pass lambda 1 through lambda 2. I have to swap them before I can hit lambda 3. So that's what this factor is here. I've just got the braiding operation telling me that I have to swap. And so sort of conceptually, this notion of braiding is very clear. It becomes very, very complicated later on as you get higher and higher algebraic structures. So this is a braided notion of braided Lie algebra. I think it was originally called a quantum Lie algebra because it was something that appeared in the language of quantum groups. But this is what I'm going to call a braided Lie algebra. And this is the basic idea of braided gauge symmetries is that they're controlled by braided Lie algebras rather than ordinary Lie algebras. And even if G is a matrix Lie algebra, this is not the same as the star commutator. So this braided Lie bracket is not the same as the star commutator because when you swap lambda 2 with lambda 1 in this bracket, you have to accompany it by this R matrix factor, which isn't there for the usual star commutator. Okay, but now you move along, you go and you start writing down the kind of kinematics of braided gauge symmetry. So if you have braided gauge fields and matter fields, they'll transform in braided representations, but now you have two types of representations. You have a notion of a left representation and a right representation. Okay, so if phi is kind of a matter field in some representation W of your Lie algebra, then the left representation will just be the deformation of the usual action of lambda on phi by the twist. And there'll be a right one where you insert R matrix factors with the intuition that you're changing the order in which it acts. Okay, and similarly for the usual gauge transformation rule. Okay, and this is something you don't see in star gauge transformations, right? Because if you swap A and lambda in the usual gauge transformation rule, you just flip the sign, so you don't have any R matrix factors appearing. But I'm not going to talk about left and right for the rest of this talk. I'm only going to concentrate on the left ones. Okay, so what else do braided gauge transformations do? Well, they don't satisfy a conventional Leibniz rule. They satisfy a braided Leibniz rule. So if I act on some sort of product of two fields, then again, I hit the gauge variation on the first field, but when I come to hit it on the second field, again, I have to do a swap. So I've got to insert R matrices. Okay, so it satisfies a braided Leibniz rule, and they close a braided Lie algebra. Okay, so they don't, so first of all, they don't close under the ordinary commutator, but you have to use what's called a braided commutator. Okay? Again, when I swap, I introduce factors of the R matrix here. Okay? But they indeed close. With this braided Lie bracket, these gauge transformations will close like this.
So Richard, I just give you a warning about 5 minutes to
oh my God, okay.
closure.
I'm going to go a little over 5 minutes, but so if people want to leave, but thanks, yeah. And so like now you can go and also define covariant derivatives. There's a notion of left and right covariant derivative in this case, and these I will use. I will use both left and right if I get to my final slide. And these are both covariant under left braided gauge transformations and right braided ones, but they're both braided gauge covariant. Okay. And now you go through, you can define a braided curvature. It's braided covariant as usual. So now it's really just looking like, putting stars everywhere. And it is, you are doing that. But there are very subtle changes to what we're doing. Then finally, of course, there are the braided diffeomorphisms, which are usually called twisted diffeomorphisms. Diffeomorphisms act by a Lie derivative. So there's a twisted Lie derivative I defined by the usual formula, and they indeed also close a braided Lie algebra. Okay, where this psi1, psi2 star is the braided deformation of the usual Lie bracket of vector fields. So that's braided gauge symmetry. And let's look at the simplest example of a braided gauge theory. And that's just the braided deformation of this Chern-Simons theory that I wrote down before. Okay, so I just take the action, I insert stars everywhere. For this theory, that's all we need to do. And then this is invariant under braided gauge transformations from this braided Lie algebra. Okay, so by demanding that things have this braided invariance, no extra degrees of freedom need to be introduced. Okay. The field equations look just like before. I used the braided curvature, no surprises. But the surprises come now when I look at the solution space. The field equations are braided covariant, but this equality I had before no longer holds. Okay, so if A is a solution of the field equations, it's not necessarily true that A plus delta lambda A is a solution. Okay, so the braided gauge transformations do not act on the classical solutions here. And there's no moduli space that you can form, no well-defined moduli space. But there are Nether identities. There's no genuine Bianchi identities, but there's a modification of the Bianchi identities using these left-right covariant derivatives. Okay, so in the classical limit, where these R factors would be 1, this bracket would just vanish on the right because it's a graded Lie bracket. So that the graded Jacobi identity would tell you that that's just 0. So we still have this notion of a braided Nether identity, which continues to hold off shell. And this is what gives the interrelationship and allows us to think about local braided symmetries as some sort of gauge redundancy in the theory. So I'm just going to explain now what the notion of a braided L-infinity algebra is. It's quite simple, actually, at this stage, because we saw how to define braided Lie algebras. And we can do the same thing with L-infinity algebras. So if we have any L-infinity algebra where the maps and the vector spaces live, are U gamma Tm modules and maps between U gamma Tm modules, so they're equivariant objects, then we can just twist the form everything and define a notion of a braided L-infinity algebra. Okay. So the formula I use is just what we usually do to deform. I take my operations Lm and then I just deform all the products that appear. Then these operations are no longer antisymmetric or graded antisymmetric, but they're braided antisymmetric. And they obey a infinite set of deformations of the usual Jacobi identities. And again, just think back to the usual Jacobi identity that I wrote down. There are now braided versions of these homotopy Jacobi identities. We can also, if we have a cyclic structure on our L-infinity algebra, we can also deform that by just usual prescription. It acts on a pair of objects, so I apply the twist to it. And an example is braided Chern-Simons theory. The braided Chern-Simons theory I just looked at can be built on a differential braided Lie algebra, whose underlying vector space is again this same vector space of formed by the differential forms on N, and with these bracket operations down here. Okay. So if you just allow me 2 or 3 extra minutes, and I will just complete the story, because now you have this notion of a braided L-infinity algebra. I said braided Chern-Simons theory is an example of that, a very simple example of that. But now you can go and give a prescription for building up braided field theories given a braided L-infinity algebra. So the formula for the gauge variation is identical to what I wrote down before, except I put stars everywhere. But because now I have these braided homotopy relations instead of bona fide homotopy relations, these close now a braided Lie algebra using this braided commutator. You can, again, for the field equations, you write down the same formula. And again, the braided homotopy identities tell you that these are covariant in a suitable sense. Okay, so there's, again, this permuting of these factors FA star with A in the brackets, which are trivial, of course, in the commutative world, but in the braided world, they're non-trivial. In general, again, there's an argument that there's no moduli space of solutions to this equation, but again, you can derive a general form of braided Nether identities, okay, which I've written here. The line in green are kind of inhomogeneous non-commutative additions to the usual Nether identities. And this is exactly what we saw in this braided Chern-Simons example. And you can, again, if you have the cyclic pairing, you can write down a version of the action. You find that it reproduces these equations of motion, and it is indeed gauge invariant. And I claim this gives a systematic construction of new examples of non-commutative field theories. The Chern-Simons example was simple. You could just introduce stars in appropriate places. But in general, that's not going to happen. This algorithm here will give you surprising new versions of non-commutative field theories, which have no new degrees of freedom. They'll have a good classical limit, and they'll be fully invariant under these braided gauge symmetries. Okay, and I just want to flash up quickly the application, which I would have spent more time on. But if you take the 4-dimensional Einstein-Cartan-Palatini gravity action, so this is treating 4-dimensional gravity as a gauge theory, you can write down, of course, the field equations, Bianchi identities, symmetries of this theory in the standard way. And from that, you can construct the corresponding L-infinity algebra, which in this example is not simply a differential graded Lie algebra like the Chern-Simons example. And then you can go and deform this in the way I just explained, deform the L infinity algebra to a braided L infinity algebra, and apply this machine to generate a braided field theory, this machine that I just very quickly went through. And you get something surprising. This is the type of theory you get. So you get a braided version of non-commutative gravity that's invariant under the braided semi-direct product of two braided Lie algebras, the braided Lie algebra of vector fields, and this braided Lie algebra of local Lorentz transformations. The modification of the field equations look like this. So now there's two notions of torsion in the non-commutative world because there were two notions of left and right covariant derivatives. So this is what the equations of motion look like. The terms in blue are what seem to differ from the classical case, but these are covariant. And what's surprising is this last line down here. This was a real surprise to us. It's each individual term is non-covariant, but the sum of the three terms conspires to be a covariant object, and these reduce to the classical field equations, which are the torsion-free condition and the Einstein equation. You can go derive the action. You find something that again differs from the naive modification of the gravity action by just inserting stars everywhere. But again, this is a gauge invariant quantity with a good classical limit. You can write down the Nether identities, which are quite complicated in this theory. But this is a new deformation of four-dimensional gravity and general relativity. And this is just a very simple example of how this construction leads to new versions of non-commutative gauge theories. Okay, I'm sorry for going over time. I'll stop there.
Thank you, Richard, for your presentation. And now we just have one or two quick questions, and then we will continue with the discussion session. But we will first two relevant or most urgent questions, please, or comments.
Or complaints.
So there is a hand raised. Let's see.
Francesco has a comment.
Yeah, maybe I can just ask. These
Yes,
Zoom
please.
tools are tricky. Yeah, I have very quick questions. First, in the last example, what is L3 classically? I mean, the
And this
higher
example,
operations, yes.
okay, I didn't write the form. I didn't write down the brackets here, but L3, you see, what happens in this theory is if you look, I mean, if you just look at the equations of motion. So look at the field equations here, right? And you've got this cubic term here. Okay, so L3 you construct but is non-zero only on fields in this theory. So omega and E. And you just, I mean, I don't have a name for it, if that's what you're asking. I mean, but you just write it.
I mean, it is constructed in using other operations like exterior, I see exterior product. Or...
Yeah. Exterior product. And yeah, I mean, all the operations here are constructed from the things that go into the definition of this classical field theory.
Okay, so and the other quick question is, okay, first of all, if there is a good reference for L infinity algebras applied to classical field theory.
Well, this paper that I mentioned way back by it's by Yurko, Saman, Wolf, and Raspellini is a good account.
Okay, and besides gravity, so in Young-Mills case, you have DG Lie algebra, or you have something more?
Yeah, no, it's not a DG Lie algebra because so Chern-Simons comes out to be a DG Lie algebra because its interactions is at most cubic, right? Yang-Mills will have a quartic interaction, so it's not a DG Lie algebra.
Okay, thanks.
Excellent, beautiful talk.
Oh, thank you, Jim. Thank you very much.
Further comments or questions?
Can I ask a question?
Of course.
Go ahead.
No. So if you consider other deformed gravity theory or non-commutative gauge theories, usually there is a way to rewrite them in ordinary language in some kind of a Seiberg-Witten expanded way. And then, so you can see that there is an extra structure coming from theta mu nu, for example. So in your new deformed braided gravity theories, is there a way to write this as some sort of an expanded version of a usual field theory? And what is the extra structure which it involves?
So let's see. So the way I'm deforming, I'm trying to think of the best way to answer this. The way if you took Yang-Mills theory based on U of N, right? And the thing I'm deforming differently, of course, is the commutator, right? I mean, it's not a star commutator, but of course, it's defined using a twist. So, with the twist, of course, you can expand this. This does have a formal expansion. So I don't know the answer to your question, Harold, but in principle, one could do this. I don't know if there's a nice answer like the Seiberg-Witten map. I suspect not.
Yeah, but I mean, if you use a twist, so for example, if you use something like a Moyal-Weil twist, then you would have the theta mu nu as a new structure. Do you expect something else, or?
What do you mean as a new structure, though? I mean, as a...
Well, from a classical physics point of view. Theta mu nu would be a two-form, which lives somewhere.
What's a bivector, you mean?
Yeah, bivector, yeah.
But it's just a parameter, right? I'm not sure I'm following.
Yeah, I mean, if you try to explain the theory to a physicist which knows nothing about these things, I mean, Seiberg-Witten is a way to do it. So I'm just, and you can sort of see what's the ingredient on top of the usual.
Yeah, I haven't thought about it, Harold. It's interesting to see if there is an answer like that. But I mean, so the key thing is that when in the conventional non-commutative theories, when you're talking about gauge symmetries, on both sides, right? The non-commutative and commutative world, the gauge symmetries are closing Lie algebras. And here in the non-commutative world, these are not closing a Lie algebra. They're closing the braided Lie algebra. So I don't know. I don't know if there's a braided version of this story, but.
Okay.
Okay, so if there's no other urgent question, I would thank Richard for his talk and ask the interested participants who have time to remain a few more minutes for further questions or comments. Thank you, Richard.
Thank you.
So
I'm going to stop now, okay? There.
Yes. So are there further questions among the audience? Yes. They are asking you to, we will ask you, the slides of your talk so you can publish it.
Okay, I'll email them to you.
Yes, thank you. So
Francesco's got his hand up.
I actually do have a question, but
Francesco has his hand up.
Yeah.
Unless it's a remnant.
Sorry?
So Francesco's got his hand up, but he might have forgot to put it down from last time.
I have a question, but if there is somebody else, better to. So I think Jim Stashev has a question, right? I saw his actual hand.
Trivial question. I'd like to know who GL is.
Somebody who wishes to remain unknown.
Gianni, you need to unmute yourself. Unmute yourself, Gianni.
Okay, it's me. It's Giovanni Landi. I'm unable to actually change my name in Zoom. Sorry, I'm really very rudimental guy. I mean, sorry. It's me. I'm in Trieste, and yeah. Okay.
So
sorry for that.
Richard, I have the following question.
Yeah.
using the twist formalism, let's say the way the Munich group has been considering in the context of quantum non-commutative reality, one can write out just on the basic of the twisting, or in modern language of braided symmetries, vacuum Einstein equations without considering a first order formalism, just looking at the second order form. This was done in the past, as you know, for the Moyal-Weil, but recently has been generalized to any kind of twist. So the question is, now there are two ways of implementing twist deformation in a way that is somehow completely coherent with the idea of braided symmetry. The second order formalism and the first order formalism that you are proposing today. It would be interesting to see whether these two theories have any relation.
Yeah, I know. I mean, we did discuss that. Yeah, we did discuss that. I mean, you know, yeah, I don't know. I don't know. I mean, like, you know, the four-dimensional theory I showed you, I mean, it looks quite different. It looks quite different from what you would naively expect. I mean, there's no way I would have guessed that you have a set of field equations that looks like that. I'm not sure if it's the same thing you mean. I mean, the idea would be to somehow, you know, do what you do in the classical case, right? That you have the first order, the equations of motion in the first order formalism. You use of course the torsion equation to solve for the spin connection in terms of the coframe, right? And then the second equation involving the curvature, of course, just becomes the usual Einstein equation, written in terms of the Levi-Civita connection. That's in principle what you would like to do. But I don't know how to do that. I don't know how. I mean, not because I think it's impossible, but I don't know.
Yeah, so
I don't know if that works. I mean, I have to say, I mean, our reason for going to the first order formalism was what I was alluding to at the beginning of the talk, was really that we were trying to understand, well, I mean, you know, the issues with the metric formalism, especially in the non-associative case. This was, you know, there's this umbrella over this talk that I didn't really stress because it's not really relevant, but, you know, it's this work we did years ago on the non-associative case, and it was trying to understand the symmetries in that theory. And of course there, it's just very difficult to work in the metric formalism. So our goal was to try to work in this, you know, the Einstein-Cartan formulation of the geometry. But then we just realized there were all these kind of caveats with looking at symmetries in that context. And one of these issues were that when you think about twisted diffeomorphisms, they don't have a kind of nice homotopy algebra interpretation. So it's kind of your philosophy you always have. Well, just twist everything. Just go and twist everything. So
maybe
as long as things close.
Maria, a comment or question.
Maria, can I add something? May I add something?
Yes, please do.
I guess what one could do is to try to do things perturbatively. I know that Richard does not want to expand anything, but if you want to really try to compare the first order formalism and the second order formalism, in theory, we could try to expand our equations, then perturbatively, then try to solve for the spin connection in terms of the Fierbeins, and then compare the result with the second order formalism. Try to write everything in terms of the metric and see, just compare the expansions of both.
Yeah, you can look like a first order or something. You can solve everything and just see if they're
first order, hopefully for first order, hopefully
but
don't go to the second order. And I think that is what Harold Steinaker was asking also. I think one can he was asking about some, if I understood correctly, like physical consequences, like in the Seiberg-Witten map. We would have to expand our equations and see what are the new terms and how they modify equations. Probably. Okay, I would expand everything.
Yeah, no, yeah. I'm not sure how easy it is still to solve things, but
No, for sure it will not be easy, but at least one could try. I mean,
yeah. No, that I mean that would certainly, that's a way to attack the problem for sure, is to see if you know, to see if you could do something at least at first order in theta, and
it would be interesting to compare, although the equations are different. I mean, what we get from the L infinity is really a different equation than the one that comes really from the one that we had before.
naive one, yeah.
Up to formal, up to field redefinitions. Or,
I don't think it's up to field redefinitions. I think it's a bit more. Okay, maybe I could also.
Yeah, I'd also think it's a bit more.
yes, that would be interesting to investigate. Anyhow, the first order corrections are, I mean, the most relevant also physically. One would look first at the first order corrections. So
Usually it's it's something that we can do, or it's let's say it's the most we can do sometimes.
Yeah, sure. Yeah. No, I mean, there's lots of questions. I mean, it's,
okay, so that is what I wanted to comment.
Thank you, Maria.
You're welcome.
thank you. So are there further questions or comments?
I have to go in about 2 minutes. So.
Yes, I know. So I'm just reading Leonardo that is greeting everybody, and I also therefore would like to thank again Richard for his very nice presentation, reaching out really the full audience of this seminar, and also all the present participants. Thank you. Thank you, Richard.
Bye-bye.
Nice seeing everybody. Bye-bye.
Bye, everybody. Bye.
Ciao, Jim.